All right. Welcome to the June Hudi Community SIG. My name is Bhavani Sudha. I'm a PMC member of the Apache Hudi project, and I take joy helping users out in Slack. You might have seen me often. And today we have a quick agenda. Like we have a few community updates, and followed by that we have a deep dive from Sydney here. Next slide, please. Yeah, so for the community updates, we have 131 pull requests authored by 60 authors in the last month. This is a screenshot from the Pulse GitHub Hudi repo. We've had like 54 closed issues, 49 new issues, and 52 open pull requests. There was one minor release, 0.13.1 from last month until yesterday. And can you go to the next slide, please, Sydney? Thank you. Yeah, we have 3,300 plus Slack users and 4,300 good GitHub stars. We have an upcoming release 0.14.0 in mid-July. We are on the way to updating our roadmap early. So early next week, you should be able to see what is going on and 0.14 and what are the new releases coming up. And we also have a new RFC since in the last 1 month. This is a Hudi reverse streamer. It's basically the opposite of Deltastreamer, where the idea is to tail like incrementally query from a Hudi source table and sync to different different applications like databases, DFS, Kafka, JDBC, etc. So I'm very excited for that. I think there is going to be more details coming out in this RFC. So please check out if you were waiting for this one or you have any feedbacks. Next slide. Yeah, so these are all various ways to join our community. If you're new to Hudi, please join our Slack. And if you love Hudi, please don't feel shy to give us a star. There are various avenues where you can approach us. There are Hudi office hours every Thursday morning, 8 a.m. to 8:30 a.m., where we have a lot of folks coming in asking us questions. There are no right or wrong questions. There are no simple or hard questions. Like, just feel free to come in if you want to see us, talk to us. There is also Slack. We try to answer questions as frequently as possible in Slack, and there are other ways you can also reach out. Okay, without further delay, I'm going to hand over to Sydney. I'll let her, can you go to the next slide, please, Sydney? So Sydney joins us from Penn Interactive, which is a online sports betting company. She is going to talk us through how they leverage Hudi in their data platform. Over to you, Sydney.
All right, thank you so much, Sudha. Thank you for the updates too in the community. So I think we're ready to get into it. So good morning, everyone. Thank you for joining today. I'm excited to have this opportunity to share our story of deploying Apache Hudi in our newly built data platform. My name is Sydney Horan, and I represent Penn Interactive and The Score. And so we're in the online gaming and sports betting industry. So it's been challenging to implement a data system that supports a very diverse range of source data and end user requirements. Our data needs to power partner reports, business intelligence, dashboards, data science, and more. And we're going to go over our team's implementation of Hudi, from how we chose it, how we got it up and running, and how we scaled it up and built systems around it. So first, to introduce our company, we're Penn Interactive and The Score, part of Penn Entertainment. And we're at the forefront of online and retail sports betting industry, catering to customers in the US and Canada. You may have heard of Barstool Sportsbook or the Score Bet, which have apps for online sports betting and casino in around 17 US states and Canadian provinces. And we span the betting domain as well as sports media. So after our two companies came together in 2022, we needed, our data engineering team needed to develop a brand new data analytics platform from scratch. And at its core, we implemented Apache Hudi. Oops, there's something popped up. Yeah, so this kind of allowed us to consolidate and analyze data from various sources, including our operational databases, with flexibility and scalability that we needed. So one of our significant challenges revolved around generating daily reports for our casino partners and marketing vendors, while also seamlessly integrating data from diverse internal sources. So to tackle this, our focus was on ensuring accurate availability of data each day, enabling us to meet our scheduled report delivery. Additionally, business intelligence is a major part of our analytics platform. So we needed dashboards and reporting systems that could provide accurate data on our financial metrics and insights for marketing and promotions teams. And then data science also leverages our data for insights and predictive analytics. And previously, our solutions for incorporating this data into our platform relied on copying the tables using either streaming or batch modes from replica databases. And those just fell short in fully leveraging the potential of change data capture. So they required batch overwriting of data and introduced operational inefficiencies. And furthermore, we also recognize the need for real-time replication into our environment that seamlessly integrated with our reporting tools, because all of our tables are queried by end users in different ways. And we needed our solution to proactively identify any anomalies in our pipelines to detect when any issues arise. So for an overview of our source data, basically comprises of dozens of Postgres operational databases owned by different service teams within our company. They have all sorts of table structures and data types that we had to be able to handle. And the volume of this data varies significantly. So in terms of change data capture messages, some tables generate 1 million messages per hour, whereas other tables generate only a few rows per year. So the variance in the data needed us to be able to scale up and down with throughput. In addition to our internal databases, we also integrate with other services through third-party file transfers, APIs, that sort of thing. And we also consume outputs from the broader data team, from models and things like that need to be ingested for downstream use. So we have Hudi jobs set up to consume those as well. For us, the overview of our target data, it starts with the raw layer, which is a mirror of the source data and is stored in S3. We store it in Parquet file format, which is efficiently written by Hudi Deltastreamer. And on top of this data, we have Redshift external tables, providing a structured layer for easy query access. And then our broader data team plays a crucial role in bringing this data into more curated layers for different purposes, like more models and creating views for in-depth analysis, and also interactive visualizations and reports. So you can see here, shows Deltastreamer, how it continuously ingests from our Kafka topics, handles all the checkpointing and deduping, and so it's able to know when it needs to resume and continue ingesting data. And this is the structure of our S3 buckets. So each database schema table gets its own directory, and then it's partitioned by date. So all the parquets land underneath each date. And on top of that, for our data team, we have the Redshift query layer. So why Apache Hudi was a good solution for us. It's a powerful data lakehouse that is designed to handle large volumes of data with ease, provides us capabilities to efficiently manage data updates and perform incremental processing, and it ensures that our data remains up to date and seamlessly integrates with our query layer. It handles our diverse data requirements from streaming CDC messages to integrating with external batch sources. And Hudi's compatibility with the rest of the Apache ecosystem was another crucial factor. We use a lot of Apache tools in our stack, and just simplifies like our data operations, how compatible everything is. And we can run Spark on our platform of choice, so we maintain flexibility with fine-tuning and controlling our pipelines to ensure performance. So Deltastreamer is an ideal solution for us for database replication. The main feature we take advantage of is the streaming of change data capture messages, which it's built to handle gracefully. So any logs emitted from the source database that tells us they updated a record is sent to our Kafka topics, and Deltastreamer knows natively what to do with these messages and applies the exact same changes to our Hudi lakehouse tables to keep them all in sync. And one of the key benefits is its parallel processing capabilities. So we have the flexibility to choose between continuous mode, which is good for high throughput and high use tables that we need near real-time data. And then the run once mode is better for smaller jobs that don't need to be constantly loading data. They have fewer updates, or they're one time a day kind of thing. So we're able to efficiently handle any sort of bulk data ingestion jobs while keeping everything consistent. And that's important because at any given time, we may have over 100 Deltastreamer jobs running to ingest from thousands of topics and around 1,000 topics and other sources. So we have flexibility to group tables together in order to save on Spark resources and a lot of other tuning things that we can do. And the other advantage is the optimized storage format. Our data is landed in Parquet, which provides efficient storage and retrieval and is able to handle updates and upserts as opposed to just appending. And with all the cleaning and archiving features at Hudi's core, we're also enhancing query performance for our data analysis and reporting tasks. So to dive into like an overview of our implementation of what our platform kind of looks like. So from a high level, we have a Confluent Cloud solution to handle the bulk of our streaming needs. First, the Debezium connectors are built to establish connections with our service team databases, captures all the CDC, change data capture events. And these are all messages coming from the database logs that are emitted whenever a row is modified, inserted, or deleted. And each event is an encoded message that represents a change to the database that we want to also apply to our database on our side to keep them matched up. And each of these events are streamed into Kafka topics that are hosted on Confluent as well. And we maintain the schema registry here. So that's what Deltastreamer uses to decode the encoded messages. In terms of our Spark platform infra, we use Google Cloud Platform for running our Hudi jobs. We're using Dataproc, which is like a managed Spark and Hadoop service on GCP for execution. And our jobs run on top of Google Kubernetes engine, which facilitates our container orchestration for deploying and managing our pods. And we use GCS for a few things, storing Hudi property files, landing zone for intermediate batch jobs, and a few other things. And then to simplify the job submission process and add the automation, we developed a Python wrapper script that's built into our project container and runs as a Kubernetes pod. It automates the Deltastreamer launches and provides flexibility for configuring the jobs for our needs. So a little more on the pipeline orchestration. Our custom Python wrapper is used in conjunction with Argo workflows. So one essential aspect of our pipeline orchestration is the pulse check and job resubmission mechanism. It basically is launched every few minutes to monitor the availability and health of our Hudi jobs. And the system automatically submits this workflow on scheduled intervals. So when a job goes down unexpectedly, it can quickly get kicked off again and ensure reliability. And Argo Workflows is our orchestration tool to help us define and execute complex workflows, along with injecting all the dependencies and variables into the Hudi jobs. And Argo helps us make sure all of our Spark resources are running and stale pods are cleaned up periodically, so everything works smoothly together. Managing data sources outside of CDC pipelines is another critical part of our ecosystem. So we have several workflows using Hudi jobs to handle and integrate this data into our reporting platform. Firstly, we have a few streamlined processes for third parties to drop files into SFTP or cloud storage locations. Some of our vendors provide us data through posts to their API. So we leverage these APIs to collect and ingest data from those sources using some custom scripts and Hudi. And then we also receive retail data from the broader company that comes from our casino on-prem data centers. So it's a little different format. We also have bidirectional data exchange with some vendors who help provide insights on some operational aspects, such as one of our marketing partners that provides us click attribution data. So for all these sources, we've developed pipelines that result in the data being inserted into Hudi tables and that represent each of the sources and is further incorporated into our analytics environment. So we've used Deltastreamer in multiple different modes. The most common pattern is the Postgres Debezium source. So this is a little walkthrough of an example of a disaster recovery scenario. Sometimes there are instances where we discover discrepancies such as duplicate, missing data due to timing or configuration issues. So when a bug is reported and the Kafka topic is beyond the expiration, we aren't able to use the normal streaming method to recover the data. So to address this issue, we've developed a workflow around a Deltastreamer job with a JDBC source. So basically, when we encounter a gap in the data, the Deltastreamer job is momentarily paused. And at this point, a JDBC job is kicked off to directly upsert the missing data into the gap from the source. And once the gap is filled, the job is resumed and everything's seamless with how the data was overwritten. And the data is back in our data lake and ready to be queried again. And so we're able to quickly repair any gaps in data and ensure our end users have the most complete and accurate information. Another big reason why we were drawn to Hudi was that being part of the Hudi community has been a critical part of our development process. Between the Slack channel, detailed documentation, quick movement on GitHub issues, weekly Zoom calls, the supportive community has been so helpful whenever we have had a question or encountered a challenge. So it's just been really nice to have access to so many experts to help with troubleshooting. Okay. Take a listen. So we're going to dive into the detailed implementation now. These are the 6 main phases of our process that we went through. I'm going to walk you through each step so we can dive a little deeper. We started with the proof of concept and making the decisions phase, and then learning how to get Hudi running and setting up the infrastructure, tailoring the package to our needs, and then streamlining all the automation, and finally figuring out how to visualize data freshness. So brace yourself because data engineering is coming. So first, during the POC phase, we brainstormed some ideas and split up the work to explore different solutions. We began by experimenting with some local Kafka clusters to just generally get the hang of how it works, test out streaming capabilities of Spark. Additionally, we developed 2 homegrown solutions that involved custom producer and consumer scripts using a local Postgres replication slot, self-managed Kafka cluster, and custom decoding of the Avro messages into a target database. So to further prove out our streaming capabilities, we tested different implementations of Debezium. We set up a local server connected to a sample database, which streamed them into a Kinesis data stream where it was consumed by a Lambda function. We also tested Debezium's capabilities for database snapshots as well as incremental ingestion. And it turned out that we each raised potential challenges with these homegrown solutions, and they all had overlapping themes. The manual handling of batch sizing and checkpointing and concerns about scalability were some of the issues we faced. And it became clear that we needed a better tool belt to accomplish our task. So that's when we started exploring Apache Hudi. To kickstart our trials with Hudi, we wrote some custom PySpark code to create data frames from Kafka topics and write it to S3. This was just to establish the connection with Redshift and make sure that we could integrate with that because it was an essential component of our existing infrastructure. So after careful evaluation, we concluded that the combination of Debezium, Kafka, and Hudi was the perfect fit for our requirements. Debezium provide reliable change data capture, and Hudi was a powerful data lakehouse, so we could seamlessly integrate with Redshift. And it was during this POC phase that we began our experimentation with Deltastreamer, which basically seemed to have all of our potential challenges baked into its core. So the next phase was setting up our, gaining the knowledge and also setting up the infrastructure to be able to run our jobs. So first we set up our GCP infrastructure with the help of our DevOps team to configure all the tools, networking, permissions. We created our Google Kubernetes engine cluster and delved into understanding how GKE and Dataproc interact with each other. We started familiarizing ourselves with running the Hudi utilities bundle as a basic Spark submit script on Dataproc to just consume it from a sample source. And as we gained more understanding, we were ready to customize the script to connect with our specific requirements, which leads us to our Confluent Cloud environment. And just a note, when we were starting to run all the Spark submit stuff, I'm sure I was using a lot of tutorials written by some of you in the audience. So comes full circle. So for the Confluent Cloud setup, we first deployed our Debezium connectors to our source databases. And we had to make sure that the Kafka topics and schema registry were working as expected. So we repointed the Spark submit script to point to that cluster instead and tested out streaming into like a local bucket, which got it working. And then finally, we configured the networking and permissions to connect to S3 so we could integrate into our Redshift cluster in AWS. So by investing all this time in learning the intricacies of Deltastreamer and getting all our environments set up, we had laid the foundation for what we needed to do next. So during the next phase, we actively were collaborating with Hudi developers to address specific challenges we had with our implementation. Initially, we were using the most recently released version of Hudi, but we closely followed all the rapid development on the repo. So we recognized an opportunity to use some of those advancements, and we decided to make a fork of our own to add custom functionality for our needs. These are a few examples of small tweaks we made and solved as part of our solution. So the first one was that our Debezium timestamps were in epic microseconds format, and this format wasn't available as a key generator. So we just had to incorporate this format as one of the config options. And then we noticed an occasional bug with multi-table jobs hanging after completion, and it was determined that these jobs were not shutting down properly due to some background services. So we worked closely with several Hudi developers to find a solution that ensured forceful shutdown of background processes if the graceful shutdown failed. So then our jobs were able to fully shut down and ready to execute again. Another issue we encountered was related to tombstone messages and Kafka topics, which are special signal messages that follow after a delete statement. And it results in a completely null value for the Kafka message. And this was because we didn't know that we had to turn them off for our first launch, and it caused null pointer exceptions. So we tried to develop our own custom transformer class, but we ended up getting a recommended code change from the Hudi developers to add a filter in the Debezium source.java file. And this removed all the null messages from the data set and got rid of our error. So some of these changes are in our fork and some are in the Apache repo itself, but these are a few extra things that went into the Hudi jar we use, and we're looking forward to integrating these changes and more into the general code base. So for the next phase was streamlining our job submission process. So we had everything running manually, Spark submit, like shell commands, and we needed to implement a solution that could ingest thousands of tables seamlessly. So this was critical in optimizing our data processing capabilities. So first, we just adopted a focused approach by targeting one database at a time. This allowed us to concentrate our efforts and make sure that we had a systematic way to build our data ingestion pipelines. So we developed a custom Python wrapper script that interacts with the Google API. And this replaced the need for all the individual shell scripts for each table and provided a more centralized approach for submitting Spark jobs. And our workflow orchestration kicks this script off every few minutes. Each time it passes arguments to the job that tells it which set of tables to kick off. This way we can control the frequency of each table and avoid overwhelming the system with too many Spark jobs. And this is a really simplified version of what the job launcher script does. First, it performs a pulse check. It gathers the list of all Deltastreamer jobs currently running and compares them to the list of jobs that should be running based on the main config file. And for each job that's required to be kicked off, we use the configs passed and some custom logic to build out all the Hudi configs and Spark arguments. So any Hudi properties that are packaged into a file, they're uploaded to GCS location, and then this is passed into the properties of the Spark job object. So when we build the Spark job object, we pass it all the information it needs to properly submit the job, the source and target locations, the payload class, Spark job size, run mode, custom configs. So this is one of the lists that gets passed to the Spark job. There's 3 other kind of lists in there. And also both of our streaming and batch Deltastreamer jobs are controlled by the same workflow. So the logic is built to distinguish between multiple modes of Deltastreamer, and all we have to do is add a new type of job to the config file, and it dynamically passes the configs to the Spark job to achieve whatever operation mode we need. So now onto the config file. We quickly noticed that there was a lot of repeatable patterns within the configs of individual jobs for Kafka topics. And the logic involved in the previous script takes advantage of these patterns by reading in the properties as dictionary items from a config file. So this file contains the distinguishing information for each source, such as key column details and the required Spark resources for each job. By organizing the table configs in this way, we have better control over the pipelines. We can add and edit and remove from this config file directly, and the launcher automation reads the latest version each time and decides what jobs to kick off and how. So considering the varying throughput and width of these tables, we had to perform comprehensive analysis for every table being ingested by looking at their expected prod throughput and assessing the needs of like the end users. And based on the analysis, we determined whether a job needed to be running 24/7 or if it could be grouped into a multi-table job. So the launcher script knows when it sees multiple tables in one job, that it should be launched as a multi-table class. And most of these tables only take a couple minutes because their sources have minimal updates, but they still need to be kept up to date, so they're scheduled on a regular cadence. It just helps us minimize our Spark resource utilization. And then to further simplify our jobs, we categorize each one based on its size, such as small, medium, large, and some other custom sizes that we had to introduce. They'll tell the tool how many Spark execs, cores, memory, and parallelism needs to pass to each job, so it's way easier to tune our Spark jobs. And having these standardized templates for job configurations has really reduced the amount of time it takes to add or modify a Deltastreamer job in our platform. So let's dive into how we built the automation and scaled out the system. So we built an Argo workflow around our orchestration script to handle the execution of the jobs. This allowed us to inject the environment variables and schedule the workflow as a cron job so it could run on schedule. And the frequency of checking the jobs is important because the single table jobs are set on continuous mode 24/7, but they can still be fragile. So in the case of an odd network timeout or Kubernetes glitch, the scheduled launcher script will quickly realize the job has failed and simply resubmit a new instance of it. So we have automations in place to clean up any failed or hanging resources that didn't get cleaned up on their own, so we can keep the system clean and running smoothly. So to do this, we started with one Argo workflow that kicked off just one of the databases in the config file that contained about 30 tables. And after this first database was up and running, we entered a phase of manual monitoring. We carefully looked into each topic being consumed to ensure the job had sufficient Spark resources, identify any config errors, such as missing columns. And we used the Spark UI as well as some GKE monitoring to make sure that everything had enough memory and solve any bottlenecks. We just wanted every job to be able to process its throughput efficiently and make sure that our job sizes were all appropriate. And we started gaining a newfound understanding for proper job size resourcing, like how a table's width and throughput affects how much CPU and memory it needs. And we found a few extra Hudi settings that we need to include. We addressed those challenges such as null pointer and other issues that arose, and we just kind of squashed all those kind of bugs. And as our knowledge and experience grew, we added more and more tables to the dictionary in our config file. And as we added more Kafka topics to that file, the workflows automatically picked up the new dictionary. We added new types of jobs to the file outside of CDC jobs. And this resulted in more and more tasks just getting deployed to our cluster automatically. So we saw our resources growing and the source data flowing, and our end users were able to start querying our Redshift data. So after all this, we needed a way to quickly identify if any of the tables started to fall behind in terms of data freshness. So we were manually checking multiple logs at first to determine if any jobs had errors or memory shortages, Spark Shuffle failure, and needed intervention. So we also created custom views on the Deltastreamer logs in Datadog using their offset. But with hundreds of tables, some of them had offsets of 5 billion and some of them had offsets of 5. So the variation made it very difficult to see the overall health of our system. We also ran scripts to monitor Kubernetes resources to check if a job's memory was too low. We built a job to scrape logs of every single Deltastreamer job and calculate stats on the timestamps of the new checkpoint strings to see if it was performing abnormally. And all this was kind of clunky and manual and takes too much time at larger scales. So to avoid these manual efforts, our data engineering team decided to build a custom monitoring system for our platform. This API continuously crawls each table in the database to retrieve its max timestamp. We then established thresholds for each table. So we were able to identify any tables that were lagging beyond what could be reasonably expected. The result of this is this user-friendly web interface that is accessible to anyone on the team. And through this interface, we can quickly get a glimpse of the status of all tables in the data lake and gauge their freshness. We can also still leverage those other tools to monitor the logging and pinpoint root causes behind any table that's lagging. So we're continuously working to integrate these monitoring abilities into a comprehensive alerting system. Our goal is to have a system that can assist an on-call engineer with debugging data latency to make sure our reports all stay on time, but ideally minimizing the need for human intervention at all. So yeah, in conclusion, the implementation of our newly built data platform at Penn has been a transformative journey and would not have been possible without Hudi. We've consolidated and efficiently housed data from various sources with high flexibility and scalability, and our experience has enabled us to provide accurate insights to our stakeholders. We're confident that Hudi will continue to play a vital role in driving the success of our data platform as we continue to integrate and grow in the sports betting industry. And I wanted to sign off on a more humorous note that applies to what we covered here today. It can be detrimental to delete a table in production, but with the power of Apache Hudi, our pipeline monitoring and disaster recovery techniques, we'd be able to detect and restore that table in less than 20 minutes. Thank you all for joining today, and I'll open it up if we have any time for questions or anything. Pass it off.
Thanks, Sydney. That was an awesome presentation. I'm sure, like all of us, have a lot of questions. I see some flowing in through the chat already. If you want to take them, we still have a few minutes, so I can probably go read the questions for the audience here. Yeah, can you share? So Paul has a question here. Can you share what types of data lake Hudi optimizations, clustering, column stats, zeroing, etc. you have used to boost Redshift query performance? Do you use Amazon Athena as well? If yes, how does Redshift perform versus Athena?
So we don't use Athena. So we've really only done testing with Redshift. And we haven't fully explored all of the optimization techniques yet. We're just kind of going to see as we go if we end up needing it and if we start experiencing lag and things like that as our data grows. So we haven't done too much on column stats and stuff besides just indexing, giving the indexes of the external tables.
Makes sense. I think Samuel had a bunch of questions. You mentioned about Redshift. Do you incrementally ingest data into Redshift and then from landing to stage? Could you talk about your approaches that you have taken?
Yeah, so we do incrementally ingest into right into S3 into the Hudi tables, and that's kind of in our raw zone, we call it. And it's like an exact mirror of the source data. And then from that raw zone, it gets moved from up towards like landing and different curated zones kind of thing. So, and those are done by other teams outside of our data lake team, and kind of it would be sort of incremental, but not as real time, I would guess. Like maybe there's going to be some views that joins a lot of the tables together, so they would remain real time, but some of them are going to be materialized tables that are produced by like DBT models, and yeah, so that's kind of our plan, what we have going. And
Got you. Thanks. I think a follow-up question from Samuel was, could you explain your backfilling strategy?
Yeah, so we figured out that we could directly connect to the database, the service databases through JDBC. And so we developed a Spark job that uses instead of Postgres to be the source, it uses JDBC source and query to pull in certain date ranges from the source database. And we pause the Hudi job, so there's no concurrent writing into the partitions, and it just upserts the data directly into that same table, and it matches like the table properties. So we have to know like all the partition keys, and then we resume the Deltastreamer streaming job, and it just catches up to however long we were paused for a few minutes, and the gap is filled. And we do the same thing if we find out that we completely didn't have a table listed at all, and we need this table now. So we just backfill the entire, like from start date to current date.
Great. I think we have more questions from Daniel. Is this tooling self-serve? I think this or centrally managed by your data function. I think Daniel was referring to the monitoring tool. Daniel, is that what you were referring to?
So more like the kind of adding to and the provisioning of this like config file that the Python wrapper uses.
Yeah, so as of now, the config file is part of our repository. So as if we have to deploy PRs and new images for the config file to get picked up, and it's just sits in the same pretty much location as the Python script that reads it. So in that way, it's kind of managed like that. But we've had some ideas in the future to like read that from a different source, like a database that hosts all the configs and the individual properties for each table, to be able to just on the fly make updates to it and automatically pick it up every few minutes instead of deploying it with CI/CD and all that.
Got you.
Thank you.
And I think Samuel had more questions. How do you determine which job is small, medium, or large?
Oh yeah, that was a fun part. So like in that first phase when we had only 30 tables, and then like a week later we had 100 tables, and we kind of just went into each of the tables and we're like, okay, this one's having so much Spark shuffle failures. Like it was a medium because we just guessed that it might need like 2 executors and 4 gigabytes or something. And then it turns out it actually was like maxing out. So on our Kubernetes charts in GCP, it shows a chart of like how much memory it's using. And if it was like always at the very top, like using 6 out of 6 gigabytes, we're like, okay, it probably needs 8. And then if it still is doing that at 8, we would give it 12 and kind of give it more machines and more cores until it finally landed at the right spot where it should be. And then, but the hard part is once it's processing so efficiently, that usage goes way down. So like, you're like, oh, now we don't need 12 gigabytes, but you actually like still do in case it gets backed up. So yeah, it's difficult. We have like XXXXL, we have large high CPU, we have large high memory, we have medium plus, like a ton of different sizes.
Gotcha. Did you have to like tag them individually, like based on different
Yeah,
onboarding, or like did you find a pattern as you like did the tuning for the first few tables?
yeah, we kind of found patterns. We made like Excel sheets of each table, how many rows it gets per minute, like projected, and how many columns it has. And we're like, okay, well, this one gets 1,000 rows per minute and has 10 columns. Like it should be grouped, like also be a medium along with these other ones. And then ones that get like way more or way less, you know, you kind of can make them smaller.
That'd be cool. All right. I think Daniel had more questions. Does Redshift require a certain data catalog in the same way Athena uses the Glue data catalog?
We kind of maintain our data catalog. So there, it's like an external schema that points to our S3 bucket. So we have external table definitions on all that. So we have a few members of our team who have been focused on managing all that. So we have config files there too that populate the DDL to create those tables. And as soon as you create the table on top of it, it's ready to be queried and taken everything in real time.
With that, have you found schema evolution a problem? I guess with Debezium, it's not. Your schemas must be fairly static for Debezium, right?
Yeah.
Okay.
So we've had some flukes when a source has like a deployment and adds a new column, and that's still something we're still trying to automate. So sometimes we get some random breaks in the data, and that's when our dashboard, you know, goes down and says that something's behind. So yeah, if they added a new column, like we want to be aware of all their deployments as well, so we can add that column to our external definition. Because if you don't add it, nothing breaks, it just won't be there.
Yeah.
Yeah.
Cool. Sorry, I got a load of questions because I've spoken to you previously in Slack, and our infrastructures are very, very similar. So I'm very jealous. Sorry, I guess I'll ask my next question. That raw zone that you are syncing to, is that append only, or do you use like upserts at all for that?
That's all upserts, so that it still is identical to the source. So if the source changes a record from December, then our job will upsert it into the December partition and change the record.
Is it a global upsert then?
I think so.
Right. Okay. Cool.
Yeah.
Nice. My final question. I promise I'll go away. Instead of using, so you're using like Spark on Kubernetes essentially, right? Is that correct?
Yeah. We had a lot of. Sorry, you go ahead. Was ever a thought to use like a single like compute entity, like an EMR cluster, and allowing dynamic allocation to remove like that small, medium, large estimation exercise? Or was there like anything that swayed you in the other way? Because we have the opposite, and I'm beginning to align more with what you've done. Was there anything in particular that changed your mind? It was just kind of in the beginning, like the initial decision we made was that a lot of our resources were already on K8s, and we just figured we could add it there. But you know, it's kind of a newer feature of Google to use to run it on GKE. That Dataproc has a few other modes too, kind of like those ephemeral clusters and just single like regular Dataproc clusters. So it's just kind of the decision we made and never looked back. And yeah, but it seems like we've got it all kind of tuned now.
Oh, nice one. Thank you very much. Any examples would be great. I was looking to use like the Spark operator on top of Kubernetes as a POC, but could never quite get it working.
Oh yeah. Yeah, I remember looking at that
Yes.
one too.
Thanks very much.
Great. I had one question, Sydney, myself. The custom monitoring dashboard, is that for all the tables in the data lake? Do you have any plans of upstreaming that? I think it is pretty useful. If you like, if you have any thoughts around that, I think the community would be like very appreciative of using leveraging that. If there is nothing like specific in there, or
Okay. Yeah, I would have to defer to our adjacent team who developed that. But yeah,
gotcha,
that it seems like it could
got,
be something useful.
gotcha. All
If
right.
I may chime in, and because I'm one of the tech leads on that other team Sydney's talking about. It's a separate service plus UI that's not really in the Hudi code base that we maintain, but maybe something we can discuss internally if there's a use case.
Makes sense. Thank you. Thank you so much.
And
All right.
Kevin, sorry.
Yeah.
I was just going to chime in on the Kevin Calanda's on my team in the chat, talking about using Redshift Spectrum for our external tables. So it's how they kind of make the connection.
Great. All right. Any other questions? Awesome. Thank you, Sydney and team, for an interesting presentation. I hope like there were like many lessons for a lot of users in the community based on your experience. Thank you all for joining us. Please reach out on Slack if you have any ideas in your mind that you want to present in Community Sync. That's all. See you the next month.
Will the slides in the recording be available?
Yes, it should be available within a day or two. We'll usually upload the recording in the Apache Hudi YouTube channel, as well as the slides should be available from the Hudi website. There is a link. I can post it in the Slack once I upload.
Perfect. Cheers. Thank you very much. Cheers.
Thank you.